So we know that orbital hybridization is useful for providing us information about molecular bonding and molecular orbitals. So just like I have hybrid cars that run on gas and electric, I can combine atomic orbitals to produce the same total number of equivalent atomic orbitals. So if I have carbon, that's our poster child for hybridization. Remember, the electron configuration is 1s2, 2s2, 2p2. I know that methane is CH4. I know carbon has 4 valence electrons because it's in the 4th group on the periodic table, right? So how many valence electrons does carbon need to have an octet? Everybody? 8. How many valence electrons does carbon need to have an octet?
6.
4. It needs 4 more. 4 plus 4 is 8. Carbon's in group 4. So, turns out, for reasons of energetics, I can promote one of these s electrons to the vacant p orbital. And remember, the reason why I don't have the 1s up here is because we're dealing with valence electrons. That's the highest energy level. So if I have 1s2, 2s2, 2p2, then I'm only concerned at looking at that second energy level. So now, in carbon hybridized, I have 1s electron in that 2s orbital and 3p electrons in the 2p atomic orbitals. And it turns out, just like I can have a car that runs on gas and electric, I can combine these orbitals in these combinations to make hybrid orbitals. So if I combine the s with the 3 2p electrons, I get an sp3 orbital. So here is an sp3 hybridized carbon. So each of these red balloons represents an sp3 electron. So look here. If I'm making an sp3 hybrid, I have the 1s, so 2s, and 3 2p orbitals, atomic orbitals, to make 4 equivalent, what I call sp3 hybrid orbitals. So each of these is an sp3 electron. So we know if I overlap this, what kind of bond do I form? So end to end? Sigma bond. And then if I bring along some 1s hydrogen, so if I had 4 of these, this is 1 electron, 1s, hydrogen, 1 electron. I get an overlap here. I form a sigma bond between the hydrogen and the carbon. I'm sharing this sp3 electron with this 1s atomic orbital. So 4 times over, I make methane. Okay? So there's methane. That's how I get that tetrahedral shape. So it turns out that if I have 4 groups attached to an atom, 4 groups attached to my carbon, in the case of methane, that's the hydrogens, I'm going to have an sp3 hybridized carbon. That molecular geometry for that molecule is going to be tetrahedral. The bond angle for tetrahedral molecular geometry is 109.5. I could also join these together, make a sigma bond, and then bring in 3 1s atomic orbitals, or my hydrogens, on each carbon to make ethane, C2H6. So then I can look at either of those carbons in that molecule, say cover up one side, and say, okay, how many, pretend if this was a single bond and I had more hydrogens, how many groups do I have attached to, say if I have this, C2H6, how many groups are attached to this carbon?
3.
No,
Wait a minute. So I've got the carbon bonded to the carbon.
2.
4?
4. Yes. 4. Hydrogens. 3 hydrogens and the 1 carbon-carbon bond. So I've got 1, 2, 3, 4 sigma bonds to each carbon. That's a tetrahedral about that carbon. So I'm looking at that carbon. Tetrahedral by that carbon. That carbon's sp3 hybridized. So if I have sp2, remember I've got 1s, 2p atomic orbitals. I hybridize them together. I've got 1p that's unhybridized. That's why I have this skinny balloons. So each of the red balloons is an sp2 electron. And this is my unhybridized p orbital. So if I then take another sp2 hybridized carbon, form a sigma bond in the middle, and then form a pi bond by overlapping the balloons above and below here. Now I've got a sigma bond here and pi bond here. If I bring in hydrogen and make the molecule ethene, so C2H4, here it is here. There's my sigma bond, pi bond. Carbon now has how many things attached to it? 3. sp2 hybridized. The shape here is going to be trigonal planar. It's a 120-degree angle. So there's my sp3, my sp2. If I have sp hybridization, that means I'm taking, back to my carbon, one S and one P. So now I'm going to have 2 things attached. So now I have an sp electron with each of these balloons. Wait a minute, nope, this is sp2. See? Now I've got an sp electron represented by these blue balloons. And now instead of just one unhybridized p orbital, I've got 2 unhybridized p orbitals. So I've got the green and the blue. So if I were to take 2 of these, I can now form my sigma bond by overlapping the red, pi bond above and below. Woo! This is a mess. And then if they hug here and back here, woo, I've got a triple bond. So pi bond here, and here, and a sigma bond here. So that's how I get ETHYNE. So C2H2. So let's look at this carbon right here. What is the hybridization of this carbon? How many groups do I have attached to the carbon? So I have, how many groups attached to the carbon? Wait a minute, don't count the bond. 2. So this is what? sp hybridized, right? And that is a linear molecule. So if I looked at carbon dioxide CO2. How many things are attached to my carbon? How many groups? 2 oxygen atoms. That carbon is sp hybridized. Linear. So this is a way to connect the molecular bonding with the molecular orbitals with the hybridization. So you're seeing how these things connect. Does that make sense? Any questions?
No.
Okay. So it turns out that I can actually go farther with this. So we learned about the 4 different sublevels. We talked about electron arrangements in the quantum mechanical model. What were those? S, P, D, and F. So what would happen if I had 5 things attached to my central atom? So if I had phosphorus pentachloride, well, this is what it would look like. We're not going to dive into what happens, because remember, we're not diving into energetically what exactly happens. We just know for reasons of energetics, we can promote electrons to the next level. So if I have phosphorus pentachloride, where did we go? Dehybrid.
So you're not going to need to know these in detail,
like.
but some of you have been
If
asking,
I
and I just
had
wanted you to know that you can have 5 or 6
sulfur
things attached to your central
hexafluoride,
atom.
so SF6, I would have a sp3d2 hybrid.